it does. Okay, so good morning, everybody. Do you hear me well? I have slightly changed my title, but everything I promised is going to come at the very end in the thermo. Is this a pointer also? Yeah, it does. Okay. So let me start acknowledging the organizers for putting up this wonderful program where we can relax and learn about Majoranas mostly. I promise I will pronounce the word after 20 minutes. Okay? So I have chosen to take graphene as the red line to talk about the different topics. And the reason is the following. In the end of 19th century and beginning of 20th century, we have been learning about metals, insulators, and semiconductors. And very few years later, we already got exotic materials, much more interesting than the ones that were known, like superconductors, and at the end of the century, quantum Hall fluids. And the 21st century has just started, and we have already been confronted with two very interesting materials, namely graphene and topological insulators and superconductors. So the question is that graphene has been the motivation for us to first be confronted in condensed matter with a material that had the Dirac cones, right? And this is very nice because it gave rise to all the rest that we are discussing now. So it's probably one of the most interesting materials that we found until now, from the point of view of technological applications and fundamental physics. But for me, the most interesting thing that graphene has brought about is the following. We knew the quantum Hall effect since the 1980s with von Klitzing. And in the 2-DAG structure, so electrons in the continuum, we had to go to 1 Kelvin to detect the quantized plateaus in the Hall conductivity. Well, however, when graphene came, simply because now we are putting these electrons in a lattice, a honeycomb lattice, but in a lattice, the same quantum Hall effect can be now observed at room temperature. So this is fascinating. You see here, so this is the Hall conductivity, measurements done by Kostanova, Zelov, and Andregaev. You see the quantized plateaus, and these measurements have been done at room temperature. So it's fascinating that you simply go out of the continuum to a lattice, and you can see now quantum effects at room temperature. This is wonderful. That's, for me, the most fascinating thing about graphene. But there is a problem, and the problem is here, 29 Tesla. This is a gigantic magnetic field. So it's nice, but not that much. But it makes you dream, right? That you could be able to see quantum effects in some material which is intrinsic at room temperature. So, as I said, graphene is very good, but nothing is only good in life. Graphene is also bad. There is no gap, so you can't do field effect transistor. It's not superconducting. Magnetism is not very spectacular, but especially, although with the work of Kane and Meillet, and also the work of Haldane, it gave rise to the topological insulator physics. It turned out to have a 2-weak spin-orbit coupling, and then we couldn't observe the quantum spin Hall effect in graphene. Well, there is a problem, because the quantum spin Hall effect is based on the spin-orbit coupling, on the intrinsic spin-orbit coupling, which is intrinsic to the material. It depends on which kind of atom you have, and carbon is too light. We need heavy atoms, so there is no way out. It's a pity. But, well, okay, you know the history. Immediately after the work by Bernevik, Hughes, and Chung proposed that we could see this effect in the mercury telluride, cadmium telluride quantum wells, and suddenly we are back to a quantum spin Hall effect, but again at 1 Kelvin, precisely like von Klitzing for the quantum Hall effect. We are back to the continuum, and we are back to 1 Kelvin. So the question is, can we push this up to room temperature? As graphene was able to do it for the quantum Hall, can we do it for the quantum spin Hall? Okay? So basically the question is, can we build some kind of artificial graphene that's going to inherit the properties of mercury telluride? So there have been several trials to build artificial graphene. It started in 2011 with the most natural one to pattern quantum dots in a 2D electron gas by the group of Vittorio Pellegrini and Aaron Pinchuk. In the beginning, these quantum dots were 100 nanometers apart, so there was no hopping in between. They have been reducing it to 50 nanometers. Nowadays, I think they are at 25, so it's quite nice. Then there was this beautiful work by Manoharan that he called molecular graphene. So he basically takes the surface states of copper 111, puts impurities that he patterns with the STM by hand with the dual lattice of the honeycomb, which is a triangular, and the electrons are repelled by the impurities and they follow a honeycomb patterning. So it's also a very nice work. And the one I am going to tell you today is this one that has been developed in Utrecht University in the Netherlands. And the experiments are done in the group of Daniel van Meckelberg. So he's a chemist. It's a colleague of mine. And it's about making synthetic graphene with semiconducting nanocrystals. This list is not exhaustive. This artificial graphene was also built with nanophotonics, and also in the field of ultra-cold atoms by the group of Klaus Engstock in Hamburg and Uhlmann Esslinger. Okay, so graphene de nano. This is a theoretical paper with our results about this system. So here you get a sketch of what is happening. You make semiconducting nanocrystals of about 4.5 nanometers, little cubes. Nature doesn't like the edges, so what nature does, the cube turns out spontaneously to be truncated. So you get surfaces 001, 110, and 111. Okay? It's just a truncated nanocube. You make many of them. You put them into a solution. This is toluene and glycol. You can't read what's written here. You put many of them into the solution and you say abracadabra. And what happens is that they self-assemble here at the interface between liquid and air. So most of the time I'm showing you the very old data. There is better data nowadays. He starts with lead selenide. These are the nanocrystals and they are 4.3 nanometers in size. Most of the time, they form square lattices when they self-assemble. But sometimes, and we don't know why, they form honeycombs, okay? And you can see these are the Bragg peaks. They are quite nice. And then what they do is, after the crystal is made, they do cation substitution. They get rid of all the lead and they replace by cadmium. So they get a crystal, a honeycomb crystal, very large, made of cadmium selenide. So it's funny because this has a different structure. One is rock salt, the other is zinc blende. But you can show that you replace everybody. But then it comes to the question, as a theoretician, you would ask, okay, if I make a honeycomb of semiconductors, does it behave like graphene, or does it behave like the constituting blocks, the semiconductors? And that's what we went on to calculate. And the answer is both. So first of all, we made a collaboration with the group of Christophe Delerue, who does first principle calculation, so atomistic tight binding, taking 10 to 6 orbitals per unit cell. And that's the band structure that you get. So the first thing is you see there is a gap around zero energy. These are the conduction bands. This is 2 electron volts where I'm starting the plot. And what you see here in the conduction band, you see that there is a Dirac cone, which has an S-like envelope, and there is a Dirac cone here in the P bands. So I got something like graphene, but with orbital degrees of freedom. You know, in graphene you have the SPX, PY, PZ electrons, but the first 3, they hybridize, they get an sp2 hybridization. So I have only 1 electron. It's PZ, but I don't see p orbital physics in graphene. Whereas here, I see this Dirac cone is being formed by px, py. So I get a Dirac cone with orbital degrees of freedom. In addition, we get flat bands. The flat bands have 2 origins. One is that the pxpy, when they go around the honeycomb, they they have a destructive interference. And the other thing is that the pz orbitals hybridize very weakly. But unfortunately, this flat band is connected to the other band. So there is a funny structure where I have something like graphene, but with orbital degrees of freedom. But then we went to look at the valence band. So now I am at negative energies. And when you look here, for someone like me working on topological insulators, I immediately get suspicious and I say, oh, this looks like a Dirac cone where you have opened a gap. So it could be topological. And we went to look for that, and indeed it is. So you can see here, they spin up and they spin down edge states inside the gap. And here are the wave functions that are localized at the edges in the ribbon. So we got a topological state for holes in the valence band of this material. So the summary for the first part is that these cadmium selenide superlattices have been experimentally realized. They have a sizable topological gap in the valence band. We have made an effective 16-band tight binding model to describe it. I will show you soon, which is published there. And you get the Dirac cones flat bands, but the flat bands are connected to the other bands, so it's not so interesting. But this opens up a fully new world, because now I can make these blocks with whatever I want, at least as a theoretician. Then the experimentalists have a hard time, but in principle I can do with whatever I want. So why not doing it with mercury telluride? Because I go to the discrete lattice with mercury telluride, okay? And that's then what we have been predicting theoretically. If I would do the same kind of structure with the same kind of size in the 5 nanometer scale, but now with mercury telluride, which has much heavier atoms and stronger spin orbit coupling, look at what happens. So this is again mercury telluride lattice in the atomistic model. This is energy in electron volts versus the high symmetry points in the Brillouin zone. And you see that this Dirac cone that I had in the p orbital now has opened a gap. And it is an enormous gap. This is 400 Kelvin. And the other thing I see is that my flat band that was there for cadmium selenide has now separated from this set of bands. It got a bit dispersive, but again, it's protected by a 600 Kelvin gap. So it's very nice. I got a flat band, and I got here something that looks like topological. So, and indeed, now I show you the comparison of our 16 bands model with the 10 to 6 orbitals first principle atomistic calculations. So we could get a very nice model that can describe the system. And you can see that indeed, when you study in both cases, you can show that this gap is topological. So simply by impinging holes in mercury telluride and patterning a honeycomb structure on the nanometer scale, you are able to get the quantum spin Hall effect at room temperatures. Now the experimentalists just have to do to realize it. It's not that easy. So the 16 bands model that we get is precisely like Kane and Melet model, with one very important difference. The intrinsic spin orbit coupling, when you have to hop next to nearest neighbors to stay within the same sublattice. Here, because I have on site sp, x, py, pz orbitals, I can connect within the same site. I don't need to hop to the next nearest neighbor. Okay, I can hop between different orbitals on the same site. And that's what makes now that my intrinsic spin orbit coupling in the p orbitals, it's 16 MeV. It's enormous. Okay, so by attributing orbital degrees of freedom to my graphene model, I got something much richer. So we have been estimating also the on-site Hubbard U and nearest neighbor interactions, and they are very large. So it's a very nice material where you could realize the quantum spin Hall effect at room temperatures. Of course, you don't need to use just these nanocrystals that we have been using. You could also pattern. You could pattern, for instance, cylinders in MB, you could grow it with cylinders which are truncated. It's very important to truncate because they have to connect through large surfaces, okay? Or you could grow spheres which are connected via cylinders. The fine details would change. In this case, for instance, which is for that one, you get a stronger Rashba that splits your spin up and down levels, but you will still get these Rose topological gaps that are quite large, okay? So it doesn't depend on the details of the structure, but it's just by creating holes inside our structure. So by summarizing this graphene, the high, we have been getting this mercury telluride superlattices, a material that in the same material you get a trivial gap at 0 energy. An S-type Dirac, so you can do all the physics of graphene if you dope with 1 electron per site for the first Dirac. A P-type topological insulator, so P-type in the sense that you have p orbitals, you are accessing p orbital physics, with a gap of 600 Kelvin. And we got a flat band, which is now separated by a robust gap from the other bands. This could be ideal to realize the fractional quantum spin Hall effect. And what is very nice is that I can go from one phase to the other by doping my system. They have not yet doped the full crystal, but by doping the individual nanocrystals, they have already achieved up to 10 electrons per unit cell. So you could easily dope and access all these higher bands. So electrolyte doping or gate doping. So it's a quite nice material, and they are trying to build that now at the moment. So these were, yes? Yeah, so in this one, we have been doing several studies, all the values. So if you look at the paper, you will see if you change the values of D compared to A. So here, my A is 1.02 D, and the D is 7 nanometers, okay? So it is all below 10 nanometers on that range. But we look at several values, and we show how the gap is varying as a function of these ratios or of these ratios, and also as a function of the truncation. It's extremely important. The truncation is very important because you want to connect via many atoms, okay? So this was then the summary about graphene the nano and graphene the high. And I had in my title graphene the pseudo, but I'm not going to tell you about graphene the pseudo because Eduardo Marino is going to tell this. It's about the role of interactions in graphene and in massive Dirac systems, the full electrodynamic interactions within a formalism called pseudo QED because of the mismatched dimensions between the electrons and the photons that intermediate their interaction. But I come now to the last part of the talk, the one I promised in the abstract, which is about graphene the hot or graphene the thermo. And this is now not only about graphene, but it's about topological systems in general. So the question that I want to ask is, can we do thermodynamics for topological insulators? Until now, we have been detecting topological states using transport, using RPS or STM, but thermodynamics, things like heat capacity, are we able to detect a topological phase by this kind of measurements? Well, people would say difficult, right? Well, first of all, I am interested in the edges. Usually in the thermodynamic limit, I make my system infinite, and now the physics I want is at the edges. And the second is a system which has non-local order parameters. I can't describe using Ginsburg-Landau. Looks like difficult. Well, we thought, okay, we have Gibbs thermodynamics, and we went to look for what Gibbs has been doing. And actually, Gibbs, at his time, he was already looking at the droplets, which had so he was interested in separating the surface from the bulk of the droplet. And the way that he did it in a very ad hoc way, as if the edge would be a different system than the bulk. And then he was putting the two of them together and saying, okay, this is my system. But we thought, we don't dare to do that. We have bulk boundary correspondence, right? How can you ever separate ad hoc the bulk from the boundary as if these would be two different systems? But just to set up our mind to understand where we are going, let me revise the standard thermodynamics. In the standard thermodynamics, we have the thermodynamics identity. And what we do is that to integrate this expression, we assume that the energy is linear in the entropy, volume, and number of particles, and then we integrate. And we get the expression like this. But now I have a system where the bulk and the boundaries behave differently. How can I do thermodynamics? So this is the way how Gibbs did. When he separates them as two systems at the same temperature and chemical potential, he will have not only the minus PdV term, but he's going to have a minus gamma dA, a term that is scaling with the surface for the boundary of his droplet. But again, he assumes linearity and integrates and gets this expression. But I don't want to assume linearity in the volume, because I want to keep the boundary of my system. I want to be able to capture non-linearities, okay? And we went to look in the literature, and we found out that actually there exists a very beautiful approach called Hill approach. There is a book about Hill thermodynamics. I don't know if has anyone ever heard about Hill thermodynamics? So Theodore Hill is a guy who died, I think, a few years ago. There is still one of his students continuing on Hill thermodynamics. But what this guy did is very nice. It's something very original. He said the following: I am going to take my big system, and I consider it as being formed by many copies of small systems. And each small system has a volume V, so any twiddle is the number of copies of my system. And each small system has a volume V. And now, what he does is, he says, okay, if I want now to change the volume of my system, the total system, I have two ways to do it. One thing is to vary the volume of the individual little ones, which are composing the big one. But another way is to vary the number of subsystems. Okay, I add another subsystem and I keep the volume constant. Okay, now, and he calls this term P hat, just in analogy to P, but it's not P, this is something else. Now you integrate at constant volume. I don't need to assume linearity anywhere. He integrates at constant temperature, chemical potential, and volume, so this term drops out, and this one now, I get this expression for the total energy. I can divide everything by any twiddle, which is the number of copies, and I get this energy per individual system. So now I got minus P hat V instead of PV. But P hat is something else. So as before, I can now connect this to the free energy, and this is going to be, as before that was minus PV, this is now going to be minus P hat V. But P hat V is not the same as PV. So it's minus PV plus something. This something, which is capturing the non-linearities in my system, he named the subdivision potential. So if everything is linear, my chi is 0. The difference between P and P hat is not there, okay? But actually, this chi is capturing the boundaries and the non-linearities which are there. It captures everything. So all the deviations from the linear behavior. And still, the connection between Hill thermodynamics with the microscopics is via the Gibbs relation. So if I know the Hamiltonian, I can take log of trace of my system, and this is going to give me my potential, my thermodynamic potential, okay? But now this is not necessarily linear in the volume anymore. So this Hill thermodynamics has been used in a few instances. For instance, to look at the glass transition in supercooled liquids, or Chamberlain. Chamberlain was the student of Hill. He has been looking at the critical scaling in ferromagnets within this description. And in 2015, people have been looking in cosmology to look at planets. And of course, they are not small systems, but because the gravitational force is very long-ranged, you can use Hill thermodynamics to describe these systems also. So we are now going to use Hill thermodynamics to study topological phase transitions, okay? And as I said, the difficulty is the edges that give us the edge states in the systems. So what we are going to do is the following. We start with an ansatz. I say that the full thermodynamic potential consists of two parts. One which is the bulk, that is scaling with the area times the length. So length is some finite width, okay? So the bulk scales with the volume, W times A, and the boundary scales only with the area. There is no W here. A can go to infinity, but the W is finite. So now what we do is the following. We know a Hamiltonian for a system. You can calculate the microscopics, you can calculate this phi. Now you take several length scales and you do a fitting. And you determine the thermodynamic potential for the bulk and for the boundary. Okay, so this is what we do. You don't need to look at the details there. And now we start looking at all the models that we know that are topological. So we looked at the CdSe chain, at the SSH model, both are one-dimensional. Then we looked in 2 dimensions at the Kane and Melet model and at the BHZ model. And we looked in 3 dimensions at the BHZ also, okay? So what do you see? I will show you the results for the CdSe and tell you what you get in the other case. Okay, so for the CdSe chain, you know your microscopic Hamiltonian, you do a Bogoliubov transformation and you go to K-space. You know that you have the 2 phases, the trivial and the topological with the Majoranas that you all love so much. And now we separate, so you do the linear scaling, you get your bulk potential and your boundary potential. And now, to classify the phase transition, what is the Ehrenfest classification? So what you do is that you are going to take derivatives of your potential and to see where you have a discontinuity. And this tells you the order of your phase transition. So you see here I'm taking the g phi g mu, and the red curve is the bulk, and the blue is the boundary. So when I take the first derivative, what I see is that there is a discontinuity at the boundary, precisely at mu equals 0.5, which is the point of the topological phase transition, but I do not see anything in the bulk. Not yet. But when I come to the second derivative, now I see that the bulk exhibits a discontinuity. So according to the Ehrenfest classification, the phase transition in the CdSe chain should be first order at the edge and second order at the bulk. It's quite nice because they occur precisely at the same point, but the jump in the free energy functional occurs at different orders. Yes? Yeah, so here is 0 temperature, but I will come to finite temperatures also. Okay? So I can detect, and I have first order at the boundaries and second order at the bulk. Good. If I do the same thing for the SSH model, I get precisely the same behavior as a function of different parameters now, but it's precisely the same feature. First order at the edge, second order at the bulk. Now, I can look at the entropy at finite temperatures, and that's quite nice. So look, I see that if I start with mu equals 0.3 and I approach the topological phase transition, which is 0.5, at mu equals 0.3, at low temperatures, I have log 2 behavior. That's the behavior of my Majorana, okay? And as I increase the temperature, I deviate from the log 2 Majorana behavior. But as I approach the topological phase transition and my gap gets smaller and smaller, I deviate from the log2 behavior faster and faster. And then precisely at mu equals 0.5, there is a jump, and now my entropy is starting at 0. Don't get nervous if the boundary term here looks negative, because it is just telling you that you are reducing further your free energy, because summed with the bulk, the total entropy is still positive, okay? And you see that this is a conformal theory, and you see that here the bulk is starting to get linear in T. So I also can now look at this generalization of the Chern number for finite temperatures. So I don't know if many of you are aware, there is a work by the group of Martín Delgado in Spain, where he talks about the Uhlmann phase. So the Uhlmann phase is a generalization of the Chern number for finite temperatures. It's a very complex concept. He has to go from pure states into mixed states. He has to enlarge his Hilbert space, and so on. It's not really a topological invariant as nice as the Chern number is, but it's a very nice construct, and for 1D, it works very well. They can define the path to understand it as a topological invariant quite nicely. So this is their work in 2D, and there is further work after that, also in 2D materials, I think, last year. So what we have been doing is we can now say, okay, at 0 temperature, so now I am plotting the derivatives of the thermodynamic potential as a function of mu. Again, one is the boundary, the other is the edge. This is the edge, this is the bulk. And I am now increasing temperature, so at 0 temperature, I had a very big spike. And now as I increase the temperature, this spike gets smoothed out, okay? So for 1 is first derivative for the blue, and for the red is second derivative, what I am plotting. So I'm plotting d n phi for n equal 1 and 2. So what you see is that now as I turn temperature on, of course, this is smoothing, but I can still define the point of this minimum. I can trace this minimum. And if I now try to plot a phase diagram, mu versus T versus temperature, and just by tracing out the minimum in this phase transition, I will get this red curve, and you don't see it in most of the parts because they are precisely on top of the green one, okay? So the green one is the calculation from Delgado for the Uhlmann phase. Knows nothing about thermodynamics. It's purely topological. And the red one is our calculation that knows nothing about topology. It is just tracing a thermodynamic phase transition as a function of temperature. And it's amazing that they fall right on top of each other. This region where they deviate, it's because it's very difficult for us as it gets very, very shallow to define what is really the minimum, okay? So all what I told you, it's for the Kitaev chain. We did the same also for the finite temperature results and for the Uhlmann phase for the SSH. And then we did the same at 0 temperature for the 2D model, so the BHZ model, the Kainen-Meillet model. Now, for those models, what happens is when I go in 2 dimensions, the order of the phase transition depends on the dimensionality. For 2-dimensional models, now what happens is that the edge has a second-order phase transition, and the bulk is third order. In 3 dimensions, the edge is third order phase transition, and the bulk is fourth order. So we have looked at 5 models, the most commonly used models, and the order of the phase transition is always going according to the dimensionality. Is this going to be true forever? Probably not. We already found a counterexample. But I will not show you the details for the BHZ. You can look at heat capacity, density of states, and so on. Detect the phase transition, so it's second order at the boundary, third order in the bulk. We can also describe a phase transition where the gap doesn't close. You just change the universality class, so you change the symmetries of your system, and you can still detect the phase transition at the edge without having anything happening at the bulk. We can also capture that. And I come then to the summary. We can describe topological states of matter via thermodynamics. The order of the phase transition is universal, only depends on the dimension of the system. And our finite temperature results compare well with the Uhlmann phase. So what comes next? We are looking now at critical exponents and trying to understand better universalities at the edge and at the bulk and crossed ones. We are looking at samarium hexaborite, which is a condo topological insulator, and this universality is not being kept anymore, has already changed, because probably you don't have any longer two bands, you have D and F electrons, the problem is more complicated. And the question is how to connect with the thermal effects and conformal field theories. So I come to the end. This was a tale about the topo. I told you about graphene, the nano, how to do artificial graphene with cadmium selenide nanocrystals. The results are published in PRX. Graphene, the high, how to get higher orbital physics in artificial mercury telluride graphene nanocrystals. And I didn't tell you about graphene, the pseudo, but I told you about graphene, the how to do Hill thermodynamics and universalities in phase transitions. Let me just fast acknowledge my collaborators. Walter Böcheling is a previous PhD student. He has been doing the 16-band model for the cadmium selenide, for the mercury telluride. Christophe Delerue and Entropy was his PhD student. They did the first principle calculations. Daniel van Mackelberg is the experimentalist doing the nanocrystals. The Brazilian pseudo-QED team Marino will show you. And then for the thermodynamics, Anton Quelle is a PhD student finishing soon in my group. Sander Kempkes has just started. This one is published, this Nature Scientific Reports. It was his master thesis, and Emilio Cobanera participated also in the first one. I thank you very much for stepping with me through this talk.
So we have time for a couple of questions.